The 30 kVA transformer, while oversized, is suitable for your application as long as the load remains within its capacity. A 60 amps disconnect is adequate. The transformer's maximum current draw is 27.3 amps at 208 volts, significantly less than the disconnect's rating. To determine conductor size, calculate the maximum current flowing through the conductors, which equals the transformer output current of 27.3 amps. Consult the National Electrical Code, or NEC, tables to find the appropriate conductor size based on voltage and current. For 208 volts and 27.3 amps, the minimum conductor size is number 10 AWG copper or number 8 AWG aluminum. Using number 10 AWG copper conductors is recommended. This offers sufficient capacity and aligns with NEC requirements. Always ensure all connections are correctly sized and torqued to specifications. Install and maintain the transformer following the manufacturer's guidelines. To elaborate on conductor sizing according to the NEC, several factors beyond just the ampacity need consideration. These include the insulation type of the conductor, the ambient temperature where the conductors are installed, and whether the conductors are bundled together or run in conduit with other current-carrying conductors. Each of these factors can influence the ampacity or current carrying capacity of the conductor. Let's delve deeper into these factors. Firstly, the insulation type of the conductor plays a crucial role. Different insulation types have different temperature ratings, indicating the maximum temperature the conductor can withstand without degrading. Common insulation types include THHN, THWN, and XHHW. THHN, for example, is a thermoplastic high heat resistant nylon coated wire with a maximum operating temperature of 90 degrees Celsius in dry locations. THWN is a thermoplastic heat and water resistant nylon coated wire with a maximum operating temperature of 75 degrees Celsius in wet locations. XHHW is a cross-linked polyethylene high heat resistant water resistant wire, typically rated for 90 degrees Celsius in dry locations and 75 degrees Celsius in wet locations. The NEC tables provide ampacity values for different conductor sizes and insulation types. It's vital to select the appropriate insulation type based on the installation environment to ensure safe and reliable operation. Secondly, ambient temperature affects the conductor's ability to dissipate heat. Higher ambient temperatures reduce the conductor's ampacity as the conductor struggles to shed heat effectively. The NEC provides correction factors to adjust the ampacity of conductors based on ambient temperature. If the ambient temperature exceeds 30 degrees Celsius, which is 86 degrees Fahrenheit, a correction factor must be applied to reduce the conductor's ampacity. For instance, if the ambient temperature is 40 degrees Celsius, which is 104 degrees Fahrenheit, and the conductor has a 90 degrees Celsius insulation rating, the correction factor might be 0.91, meaning the conductor's ampacity must be reduced by 9%. Thirdly, the number of current-carrying conductors bundled together in a conduit or cable also impacts ampacity. When multiple conductors are bundled together, they generate heat, which can raise the overall temperature within the conduit or cable. This increased temperature reduces the ability of individual conductors to dissipate heat, lowering their ampacity. The NEC provides adjustment factors to account for this dirting. If more than 3 current-carrying conductors are bundled together, an adjustment factor must be applied. For example, if there are 4 to 6 current-carrying conductors, the adjustment factor might be 0.80, reducing the ampacity by 20%. These adjustment factors are cumulative, meaning that if both ambient temperature and bundling affect the installation, both correction factors must be applied. Therefore, to accurately determine the appropriate conductor size, one must consider the conductor's insulation type, the ambient temperature, and the number of current-carrying conductors bundled together. Consulting the NEC tables and applying the appropriate correction and adjustment factors will ensure that the conductors are adequately sized for the intended application, promoting safety and preventing overheating. In this specific scenario, with the Labvolt A frames, even though the calculated current is 27.3 amps, it's good practice to account for these factors. Given the recommendation of number 10 AWG copper, which typically has an ampacity of around 30 amps with a 75 degrees Celsius insulation, there is some built-in safety margin. However, if the conductors are run in a hot environment or bundled with other conductors, a larger conductor size, such as number 8 AWG copper, might be a better choice. Proper overcurrent protection is also crucial. The overcurrent protection device, such as a circuit breaker or fuse, should be sized to protect the conductors from overload and short circuits. The NEC specifies that the overcurrent protection device should not exceed the ampacity of the conductors. In this case, a 30 amp circuit breaker or fuse would be appropriate for number 10 AWG copper. However, it's essential to check the specific ratings of the equipment being powered, such as the Labvolt A frames, to ensure that the overcurrent protection device is compatible. Additionally, grounding is a critical aspect of electrical safety. The grounding system provides a low impedance path for fault current to return to the source, allowing the overcurrent protection device to trip and clear the fault. The NEC specifies the requirements for grounding and bonding, including the size of the grounding conductors. A separate equipment grounding conductor, or EC, should be run with the circuit conductors to ground the metal parts of the equipment. The size of the EGC is typically based on the size of the circuit conductors. For number 10 AWG copper circuit conductors, a number 12 AWG copper EGC is generally sufficient. Furthermore, bonding is essential to ensure that all metal parts of the electrical system are electrically connected, creating an equipotential plane. This helps to minimize voltage differences and reduce the risk of electric shock. Bonding should be done in accordance with the NEC requirements, using appropriate bonding jumpers and connectors. Transformer connections are also important to address. For a 240 volts 3-phase delta to 208 volts 3-phase Y transformer connection, understanding the voltage and current relationships is crucial. On the 240 volts delta primary side, the line voltage is equal to the phase voltage. On the 208 volts Y secondary side, the line voltage is 208 volts, and the phase voltage is 208 volts divided by the square root of 3, which is approximately 120 volts. The current on each side of the transformer is inversely proportional to the voltage. Since the transformer is rated at 30 kVA, we can calculate the primary and secondary currents using the following formulas. Firstly, the primary current equals the kVA times 1000 divided by the square root of 3 times the primary voltage. The primary current equals 30 times 1000 divided by the square root of 3 times 240 volts. The primary current equals approximately 72.2 amps. Secondly, the secondary current equals the kVA times 1000 divided by the square root of 3 times the secondary voltage. The secondary current equals 30 times 1000 divided by the square root of 3 times 208 volts. The secondary current equals approximately 83.3 amps. These calculations are essential for selecting the appropriate overcurrent protection and conductor sizes for both the primary and secondary sides of the transformer. Considering the information provided, the 60 amps disconnect on the primary side is undersized for the calculated primary current of 72.2 amps. While the actual load of the Labvolt A frames might be significantly less, the disconnect should be sized to handle the full potential current of the transformer. A larger disconnect, such as an 80 amps or 100 amps disconnect, would be more appropriate. In summary, while the 30 kVA transformer can be used, ensuring proper sizing of all components and adherence to NEC guidelines is vital for safe and reliable operation. This includes verifying the disconnect size, conductor sizes, overcurrent protection, grounding, bonding, and transformer connections. Proper installation and regular maintenance are equally important to ensure the longevity and safety of the electrical system. Remember to consult with a qualified electrician to ensure that all work is performed in accordance with local codes and regulations. Lastly, documentation is very important. Keeping records of all calculations, conductor sizes, overcurrent protection ratings, and grounding and bonding connections is crucial for future reference and maintenance. This documentation should be readily accessible and updated as needed. Proper documentation can aid in troubleshooting and prevent future electrical problems. It's also important to label all electrical components clearly and accurately. Labels should identify the voltage, current, and function of each component, making it easier to understand the system and perform maintenance. In addition to following the NEC, it's also important to adhere to any local electrical codes or regulations that may be in place. Local codes may have additional requirements or restrictions that must be followed. Always check with the local authorities to ensure compliance. Regular inspections of the electrical system are essential to identify any potential problems before they become serious. Inspections should be performed by a qualified electrician and should include checking for loose connections, damaged conductors, and signs of overheating. Any issues identified during the inspection should be addressed promptly. Finally, safety should always be the top priority when working with electricity. Always to energize circuits before working on them and use appropriate personal protective equipment, such as gloves and safety glasses. If you are not comfortable working with electricity, it's best to hire a qualified electrician to perform the work.